In this class, I will first give you the solution for the quiz 3 and then give you a brief review for the final exam. The first problem is based on the time-dependent reactor behavior. So we have a control rod adjustment introduce a power rise on a period of t is equal to 200 seconds. How long does it take to double the reactor's thermal power? So the reactor's thermal power will follow this equation. So Pt over P0 is equal to this exponential function. So exponent T over capital T. This capital T is the reactor period, which is given as 200 seconds. And this T, lowercase t, is the duration of time, and which is requested by the problem. So the thermal power is doubled. Then we have the Pt final power over P0 initial power will be 2. Then we solve this equation, we can get the t is equal to 138 seconds. Okay. Problem B. With the value of beta total is equal to 0.008 and tau is equal to 13 seconds, estimate the delta K or rho produced by the rod shift. So for this problem, we have the control minor adjustment. So it means that the introduced reactivity will be relatively small compared to the beta. Therefore, for the rho that is much smaller than the beta, the reactor period t is equal to this equation. If the rho is larger than beta, we have another equation, which I will show later in this course. So the t is 200 seconds, and the beta is given as 0.008. If the beta is not given, then we have the default value, 0.0065. The tau here is 13 seconds, and if the tau is not given, then we have another default value. Then we rearrange this equation. We want to calculate the rho, that is the introduced reactivity. So move the rho to the left hand side, then move the t to the right hand side. Then we calculate that. We have the reactivity rho is equal to this value. This reactivity has no unit. Okay. Problem C. What is the reactivity expressed in terms of dollars and cents? Okay. So reactivity may be expressed in different units. For dollar and cent, we simply use the actual reactivity to divide the beta t, beta total. In this case, beta t is equal to 0.008. Then we use this one over this one. The result will have the dollar unit. Okay, we have dollar unit. Then that is $0.065. Then we can also multiply by 100 to convert this one to cents. That is 6.5 cents. So either way will be correct. Next problem. A uranium-235 filled reactor has a rated thermal power of 3200 megawatt. It has been operated for 2 years with a capacity factor of 90%. What is the mass of 235 consumed? We know that the 235 consumption rate is 1.3 megawatt a day. So here we know that to produce 1 megawatt a day heat, it will consume 1.3 gram of the fuel. Therefore, we just need to calculate how many megawatt a day of thermal energy is produced over 2 years of operation. So the solution is that we calculate the total energy produced over 2 years. So E is equal to the rated thermal power, 3200 megawatt, then times the capacity factor, so that is the actual thermal power, then times the number of days of the operation, so times 2 years, then times 365 days. then we get the number of megawatt a day produced. So this is the energy unit, okay, energy unit. And we can also convert the megawatt a day to joule for the second problem, okay, because second problem we need to make the unit to be consistent. So to convert megawatt a day, we convert the megawatt to watt, okay, convert the megawatt to watt. Then convert the day to seconds, okay, convert day to seconds. So the watt times the second will give you the joule. So one day is 24 hours, then each hour contains 3600 seconds. Okay, so this is number of joules. Then go back to this problem A. Go back to the problem A, and the uranium-235 consumption will be the amount of megawatt a day times 1.3. So the result will give you a gram. Then we convert the gram to tons, okay, to metric tons. So this is the amount of uranium-235 consumed. Then go to the next one. So if all heat energy is to be provided by nuclear fusion using the following DT reactions, okay, assuming all released energy can be recovered, what is the mass of total fusion fuel consumed? So we know the atomic mass for deuterium, we also know the atomic mass for the tritium. So for each reaction, the total energy release will be 3.5 plus 14.1. Okay, we assume all those energy are recoverable. So total fusion reaction, total energy released per fusion reaction is 3.5 plus 14.1, that is 17.6 MeV. We need to convert the MeV to joule. Okay, use 17.6 times this factor. So we convert this MeV to joule. So for one fusion reaction, it will release this small amount of energy. Okay. Then we need to determine how many fusion reactions are needed to produce this amount of energy. Okay, how many fusion reactions are needed to produce this amount of energy? Okay. So we use this amount of energy, 1.8 times 10 to 17 joule, divide fusion energy release per reaction. So we can get this number of reactions. Okay, this number of reactions. We then convert this number of reactions to moles, because this number of reactions is equal to the same number of deuterium atoms and the same number of tritium atoms. So we convert the number of atoms to number of moles. We use the total number of atoms divide the Avogadro number. So it will require this number of moles. For each reaction, it will consume, for 1 mole of fusion fuel, the mass is mass of deuterium plus the mass of tritium. Okay. Therefore, we use this number of moles times the gram per mole, so we get the total mass consumed for the fusion fuel. And the result will be in gram, then we convert the gram to kilogram. Then you compare this value with the 235 consumption, you will see that the fusion energy will be more efficient than the fission reaction. Next problem. A reactor of 3200 megawatt thermal has been operated for 1.5 years. Then it is shut down for maintenance. How long after the shutdown does the reactor produce 1 terajoule of decay heat? Okay, so after reactor shutdown, it will continue to produce the decay heat. it will continue to produce the decay heat. And at what time the total amount of decay heat produced is equal to 1 terajoule. Okay. So the reactor has been operated for 1.5 years, so that is relatively quite a long time compared to the time period after shutdown. So we can assume that the reactor has been operated for infinite amount of time. Then we can use the simplified formula. So we have the Q, that is total heat produced, which is 1 terajoule, is equal to the integration of power. Okay, integration of power, you get the heat. Okay, because the power times the duration of time, you get the heat. In this case, the power is a function of time, therefore we need to perform the integration. Then this p tau, we replace this p tau function as p0 times 0.07 times tau to the power of negative 0.2. Okay, so we integrate this part with respect to the tau. Then we integrate from 0 to certain time, unknown time t. Then use your calculus knowledge. Also in the class, we already give you this solution. Will be this one. Can be this one. Then we evaluate this formula from 0 to t. Okay, so we replace the tau by the t. That's the first part. Minus replace everything. Replace the tau by the 0. You get another part, which is 0 in this case. Then you do some calculation. So the P0 will be 3200 megawatt. Then we get this value. Because here for the power we use the megawatt. Therefore the total heat we need to use the megajoule. Okay. 1 terajoule is equal to 1000 gigajoule. Then 1 giga is equal to 1000 mega. So 1 tera is equal to 10 to 6 mega. Okay. Then you solve the t. Then t will be this value. The unit will be seconds. Then you convert the seconds to the hours, which will be easier for the reader to understand. So after 7.7 hours, after reactor shutdown, the reactor has produced 1 terajoule of decay heat. Okay. So that is the problem A. Problem B. What is the reactor thermal power at that time? Okay. Basically, we just need to use this power formula again. Okay, so PT, that is the power, decay power at a certain time after shutdown, is equal to P0, that is the initial power, 3200 megawatt. And this T will be this 27,600 seconds. Okay, then the result will follow this megawatt unit. Then that is roughly 29 megawatt. So after roughly 8 hours, the reactor is still producing 29 megawatt of thermal power. So this will conclude the quiz solution. If you still have a question regarding any of the quiz problem or any other homework problem, feel free to contact me or contact the TA. We are happy to give you further explanation. Next, we move to the final exam review. First, the date and time will follow the TAMUK official final exam schedule. That will be Monday, May 11 from 8 to 10:30 a.m. Make sure you get up on time. Okay. There will be 4 calculation problems. Okay. The exam will only contain the calculation problem. Okay. You need to log on the Blackboard and complete your final exam there, just like how you did your quiz 3. Okay. To complete this exam, you can either type your answers to the text box provided by the exam. And most of the students completed the quiz 3 in this way. Alternatively, you can also upload a clear scan of your handwriting document, because some students prefer writing on the paper. So that is okay, totally okay, totally okay for the exam. And I added another question that will allow the file upload. Okay. So if you choose to upload the scan, you must combine all your files. If you have multiple photos, you have to combine all those photos into one single file. You can do that. You can make a zip file to contain multiple separated photos. That is fine. You can also convert everything to a PDF file with multiple pages. That is also okay. You must combine all the files you want to upload to a single document, because the upload window will only allow a single document to be uploaded. Subsequent attachment will overwrite the previous attachment. Okay, you can only upload one file, so this is important. For all those questions, you can collect all your scans, all the solution to all the questions, and upload all your solution to the last problem, okay, which will be the only place where you can upload the files. And the exam is open book and open note, okay, and you should not communicate with other students. If you are unable to make to this exam, you need to contact me one day, at least one day before the exam, so that we can reschedule your exam. If you are doing the exam at a different time, you may have a different version of the exam. Okay. To review this final exam, first you need to review all the homework, and also the quiz 3, and also you need to review all the class examples. Not all the class examples are repeated in the homework. Okay. The exam will only cover the knowledge we have studied after the midterm. Okay. In the following slides, I will summarize the important equations that may be covered by the exam. Not all the equations used in the exam are explained here. Okay. First, we start from the chapter 20, time-dependent reactor behavior. And in this chapter, we have some important concept. First one is the beta total, okay, delayed neutron fraction, total delayed neutron fraction. For the uranium-filled thermonuclear reactor, thermoneutron reactor, the beta T is equal to 0.0065 and tau is equal to 12.7 seconds. If the problem gives you other value, then use the value provided by the problem. Otherwise, you may use these two values as the default value. We also have the introduced reactivity, and the introduced reactivity may be expressed in delta T, may also be expressed in the reactivity rho. Okay. For small reactivity insertion, the delta T and the rho are very close to each other, and in most of the cases, these two concepts are interchangeable. We need to calculate the reactor period T. This reactor period T has two branches. If the delta K or the rho is much smaller than the beta, then we calculate delta T according to this formula. If the delta K is larger than beta, then we calculate the delta T, we calculate the reactor period according to this formula. This LP is the prime neutron lifetime. Okay. After you have the reactor period, then you can calculate reactor power. Reactor power at a certain time t will follow this equation. Okay, follow this equation. So reactivity unit may be expressed in the no unit value, or may be expressed in the dollar and cent. There's another unit called PCM, percent milliroom. Okay, review those concepts. In this chapter, we also have another two formula that will let you estimate the reactivity feedback. Okay. One is for the temperature feedback, another one is the power feedback. For example, if the temperature of the fuel or temperature of the coolant is increased by a certain degree, then you can calculate what is the reactivity introduced. And we can also have the power formula. Okay, power formula. In this chapter, we also have the control rod worth. Okay, control rod worth, that is the reactivity inserted by this control rod. So the control rod, we may have different depths. That Z is the depth. So Z may be 0. If Z is 0, it means that the control rod is completely withdrawn. Then if Z is equal to H, that is core height, then the control rod is fully inserted. Okay. If the Z value is larger, then you have the control rod inserted deeper into the core. When using this formula, you need to understand the meaning of each variable. So the rho Z, that is the actual control rod worth for certain insertion depth Z. Rho T is the total control rod worth if it is fully inserted. Okay. Then Z is the insertion depth. H is the total core height. Okay, core height. When you calculate this sine function, make sure that you convert your calculator to red mode, because in this bracket you get the red. Okay. Then the delta rho is equal to rho Z initial minus rho Z final. If you have the control rod movement from one position to another position, then the change of the reactivity can be calculated by this formula. Okay. Next one is the one factor. Okay, one factor. To produce 1 megawatt a day of heat, 1.3 gram of the 235 is consumed. Okay. The last concept is the uranium enrichment. You need to know how the uranium enrichment is defined. The uranium enrichment is defined as the mass of uranium-235 over the total mass of all uranium. Next, we move to chapter 21, reactor safety and security. The first part is how to calculate the reactor decay power. So after the reactor is shut down, the reactor is still producing power from the radioactive decay. So the reactor decay power can be calculated by this formula. In this formula, the PT is the decay power after T seconds after shutdown. T seconds after shutdown. P0 is the reactor power, thermal power before shutdown. And capital T is the reactor operating time before shutdown in seconds. And T is the seconds after shutdown. If the T is large, then this equation can be simplified to this formula, so that if the T is very large, so we can ignore the last term here. Then the total decay heat produced within T seconds after shutdown can be calculated by this formula if the T is large, if the capital T is large. Okay. We also use this formula in quiz 3 and also use this formula, introduce this formula in the class. The next topic is the event tree and fault tree. And based on event tree and fault tree, perform the risk calculation. Okay. And another formula that may be useful is the specific heat equation. Okay. So here the Q is the total amount of heat absorbed by this material. And M is the mass of the material. Cp is the specific heat, and delta T is the change of the temperature. The following chapters does not introduce new equations, but give you some concept for different scenarios. For nuclear propulsion, you need to know how to calculate the consumption of uranium-235 from propulsion reactor operation. Okay. Another topic is the radioisotopic power. For chapter 23, radioactive waste disposal and fusion reactor, you just need to review the homework and the class example. Okay. For nuclear weapon, you need to know how to calculate the nuclear fuel blend, mix two different types of the fuel and produce another type of the fuel for different enrichment. Then review the concept of reaction rate and the number of reactions and also the TNT equivalent and so on. This will conclude the final exam review. And thanks for attending this class, and good luck to all your finals.